Hello everyone, how are you all? I hope you all are well. So welcome back to our new video. So in our previous video we have already discussed one of the colligative property from the chapter solution, that is the relative lowering of vapor pressure. Now we are going to move further and we are going to see some more colligative properties. So today we are going to discuss our next colligative property, but if you haven't seen that video in which we have discussed about relative lowering of vapor pressure, just click on I button and just see that. Okay, so let's move to our next colligative property, which is the elevation in boiling point. Okay, so this is again a colligative property as discussed earlier. Colligative property is a property in a solution where the property is going to depend on the moles of solute, okay, which is when added in a solvent to prepare a solution. It will affect the vapor pressure, elevation in boiling point, freezing point and osmotic pressure. So let's see it one by one, but already we have done the relative lowering of vapor pressure. So today our next property is elevation in boiling point. Now when we are saying elevation, elevation means increase. So boiling point is going to increase, and that is for what? Solution. Now why the boiling point is going to increase? Because what we are going to do here, we will be adding a non-volatile solute. Okay, we will be using the non-volatile solute again, and we will be adding this non-volatile solute in a solution. Now you all know, if suppose we are going to add a non-volatile solute in a solution, the vapor pressure, that is the vapor pressure of solution, is going to decrease. Okay, that is vapor pressure is going to be decreased. You all know that. So that decrease in vapor pressure will be automatically going to affect the elevation in boiling point. How? We are going to understand with the help of this graph. You can see it here. So we'll be drawing a graph, okay, like this kind of graph is there, where this axis we are representing it as vapor pressure, okay, and this axis will be representing temperature. Okay, so first of all we are going to see the graph for the vapor pressure of solvent, that is pure solvent, that is when we have not added the non-volatile solute in it. So as we have not added any non-volatile solute, so the vapor pressure will be in a vapor pressure of the solvent is in a pure form, is going to be like this. Suppose this is a graph in form of a curve for the vapor pressure of pure solvent. So we'll be writing it here, vapor pressure of pure solvent. Suppose this is a graph for the vapor pressure for the pure solvent. Now as already discussed, when we add a non-volatile solute, the vapor pressure of the solution is going to get reduced. So when we are going to draw the graph, a similar kind of a curve for the vapor pressure of solution, then automatically the vapor pressure is going to be less for in such case. That is, it will be coming down like this. Okay, so suppose this is V dot P. V dot P means vapor pressure of solution, because now we have added a non-volatile solute. So I am mentioning here this solution is having a non-volatile solute, okay, and because of this the vapor pressure is going to be down. Now now the term comes the boiling point, how it is going to affect the boiling point. For understanding that, you must understand the definition of the boiling point. Now what is the definition of the boiling point? First of all, that we are going to see boiling point. Boiling point means it is the temperature, okay, temperature at which at which the vapor pressure of liquid, okay, any vapor pressure of liquid will be equal to atmospheric pressure. Okay, the temperature at which the vapor pressure of liquid will be equivalent to the atmospheric pressure, that is its boiling point. Now if you see, the vapor pressure of pure solvent is quite higher. Okay, so when the vapor pressure of pure solvent is going to be quite higher, so suppose this is the point where we are considering any vapor pressure of pure solvent, and then we are going to calculate its temperature. So it will be coming like here, T naught B. Why I am mentioning it as T naught B? Because it is a vapor pressure of pure component, that is pure solvent. Okay, so this is the temperature where the vapor pressure of pure solvent is suppose coming equivalent to the atmospheric pressure. Okay, okay, so that is one thing. Now when you see the vapor pressure of the similar vapor pressure of the other component, that is vapor pressure of solution we are talking about, where we have already added non-volatile solute, then what you will find that the vapor pressure of the solution is going to be like this, that is going to be TB for the same case. Okay, suppose at this point the atmospheric pressure and the vapor pressure of solution is going to get equivalent, like as they did in the case of the pure solvent. At any point of the graph we can draw like this, and this is the boiling point, or this is the temperature of the boiling point coming for the vapor pressure of solution. So as we know, this is the axis we are using for temperature, so you can easily understand that the new boiling point, that is the boiling point of solution, is going to be more as compared to the boiling point of pure solvent, and the difference between them is known as delta TB, which is the elevation in B dot P. B dot P is not blood pressure, boiling point. Okay, so delta TB is coming here, the elevation in boiling point, which is the difference between the two boiling point, and you can easily see from the graph, okay, that is the boiling point of the solution is going to be quite higher as compared to boiling point of the pure solvent. Okay, so it means that when you have added a non-volatile solute in a solvent, its boiling point is going to get rise, which is known as elevation in boiling point. You can understand it in a very simple way also, because suppose if solvent is there, you have heated it at a specific temperature, its vapor is going to form and will create vapor pressure. But when you have added a non-volatile solute, as it is a non-volatile, it will not evaporate. So you have to increase the temperature to make them evaporate or to create some pressure. So when both the pressure become equivalent, that there will be certainly the difference between their boiling point is going to be there, which is denoted as delta TB, which is elevation in boiling point, and you can represent it as delta TB will be equivalent to TB minus T naught B, that is elevation in boiling point. Okay, understand? Now when so the relationship between this elevation in boiling point and the amount of the solute added, there is a one relationship between them is there, which is that elevation in boiling point, that is delta TB, is proportional to small m. Okay, if you remember small m is molality of solution. Okay, so it means you can write it like this, that is delta TB will be equivalent to m, and now when we are removing the sign of proportionality with equivalence, there will be some constant which is Kb. Okay, the constant is going to be Kb. Kb is molar elevation constant. Okay, molar elevation constant, and its value is going to be fixed for a certain solution. okay, certain solvent, as we can say. So the final formula which we are going to have, that is delta TB equivalent to KB, and the formula for molality you can use, that is WB, that is a given weight of solute, divided by MB, that is a given weight of, that is molar weight of the solute, multiplied by WA, which is a given mass of solvent, multiplied by 1000. If the mass of the solvent which is given will be in gram, then it should be converted in kg. So that's why we have used 1000. So this is going to be the final formula for finding the elevation in boiling point by using the mass of the solute given, that is non-volatile solute mass. Okay, and hence we can calculate the value of elevation in boiling point. If you are provided with the temperature or boiling point of any of the component, you can use this formula, and then you can calculate it by using the elevation in boiling point. Okay, suppose you have calculated elevation in boiling point, and after that, suppose you have to find the vapor pressure of pure solvent, and the boiling point of the solution is given to you, then you can put all those values here and you can find it. So that is how our second colligative property is going to be there. So that is, by addition of non-volatile solute, the vapor pressure is going to rise, which automatically results in the rising of boiling point of the solution. Okay, and that is going to be the relationship between them. Okay, so now students, we are going to see our third colligative property, that is depression in freezing point. So let's see that. Okay, so now students, we are going to see the depression in freezing point, that is our next colligative property. When you are going to observe the formula for the depression in freezing point, it is going to be quite similar to the one which we have discussed earlier, that is elevation in boiling point. And the factor which is going to affect this depression is again the same thing, that we are going to add a, what we are going to add, a non-volatile solute. Okay, this non-volatile solute is creating everything, that is the elevation in boiling point, that is depression in freezing point, and that is the relatively lowering of vapor pressure. And when automatically, because when non-volatile solute you are adding and it causes the relative low, that is the lowering of vapor pressure, it will affect other properties also. Okay, so let's see the depression in freezing point. So that also we are going to understand with the help of a graph. But before understanding the graph, we have to see the definition of freezing point, like we did for the boiling point also. Okay, freezing point. Now what is this freezing point? Freezing point is a temperature, okay, at which temp dot temperature at which the vapor pressure, again the role of vapor pressure is very important. The vapor pressure, that is V dot P, of liquid, okay, liquid means any substance, okay, whose vapor pressure we can find out. So vapor pressure of liquid is equivalent to vapor pressure of solid state of same liquid. Okay, you understand? That is, the temperature at which the vapor pressure of the liquid substance is equivalent to the vapor pressure of the solid state, means so of that same substance, that same liquid I am talking about. So the vapor pressure in the liquid state and the solid state will become equivalent. So the temperature at which it will occur is known as the freezing point of that liquid, okay, or freezing point of that substance. So when the vapor pressure of liquid state and solid state of same substance become equivalent, then it is known as the freezing point of that substance. Okay, so now how it is going to be affected with the addition of non-volatile solute, we are going to see that. Okay, already discussed, when you add non-volatile solute, the vapor pressure is going to get reduced, and that will play an important role. So let's understand with the help of a graph. So we'll be drawing a graph, the similar type of graph as we have drawn in the case of the elevation in boiling point. This is going to be our vapor pressure, and suppose, and this is going to be our temperature. Okay, Now suppose this is the vapor pressure of pure solvent, okay, in liquid state. Okay, when the solvent is in the liquid state, then suppose this is the vapor pressure of pure solvent. Okay, now we have added non-volatile solute. Now non-volatile solute did what? It will decrease the vapor pressure, okay, and this become the vapor pressure of solution, okay, because now the vapor pressure is going to get reduced because of the addition of non-volatile solute, so the graph is going to come down. Okay, so this is going to be the vapor pressure of solution, okay, like we did in the case of the elevation in boiling point. Now we are here talking about the freezing point, and freezing point means the vapor pressure of liquid and solid state become equivalent. Suppose this is going to be the graph for, I am drawing another graph here, you can see this graph. This is the graph for vapor pressure of solid solvent, when the solvent becomes solid, and this is the vapor pressure of solid solvent, suppose. Okay, so at this point suppose the vapor pressure of solid solvent and vapor pressure of pure solvent in liquid state become equivalent. So this is going to be the, when you see in this axis, that is temperature, the freezing point of solvent, that is pure component, and that will be represented as T naught F. Okay, so what it is the freezing point, okay, freezing point of pure solvent. Okay, so that you understand, that is the vapor pressure of solid solvent and liquid state is coming equivalent at this point. So the, according to this, the temperature will be coming T naught F, which is freezing point of pure solvent. Now same is going to happen for the vapor pressure of solution. So if solution is required to be freezed, then its vapor pressure of solution and the vapor pressure in the of the solid solvent should come equivalent. And suppose at this point you can see, when you move the graph further, at this point they are going to meet. So it means at this point the vapor pressure of solid and vapor pressure of solution is coming equivalent to each other. So when you draw a line down, you will find that this is going to be the point, that is the temperature at which this solution is going to get freeze. So this point is represented by TF, okay, because this is solution's freezing point. So this is known as the solution freezing point. Okay, so you can easily observe that here T naught F, that is freezing point of the pure solvent, is greater than the freezing point of solution as it is coming here. So the difference between the two, that is TF and T naught F, will be known as delta TF. Okay, delta TF, that is like this we can represent. Okay, and it is known as depression in freezing point. Okay, so it is known as depression in freezing point, and again it is going to be the difference of the freezing point of two component, but this time the freezing point of pure component is more, so it will be T naught F minus TF. Okay, that is freezing point of pure component minus freezing point of solution. Now again, this property is depending upon the amount of the solute added in a, that is non-volatile solute added in a solvent. So delta TF is going to be proportional to small m, where m means molality of solution, or when you remove the sign of proportionality, a constant will appear which is Kf, and Kf is known as molar depression constant. Okay, molar depression constant, And final formula, if you write the formula of the molality also here, it become KF given weight of non-volatile solute, MB molar mass of non-volatile solute, WA given mass of the solvent. If it is in gram, then 1000 will also appear, which appear most of the time. That's why I'm writing. If it is in kg, no need to write 1000. Okay, so this is going to be our final formula. Also, you can find the unit for the molar elevation constant. So as you know, Kf will be equivalent to m, that is molality, upon delta Tf, that is a depression in freezing point. Molality unit is, if you remember, that will be mole per kg, okay, inverse, like that. And the Tf is in Kelvin, so it will be Kelvin inverse. That is temperature we are always going to measure in Kelvin. So that is how you can find the unit for Kf also. Okay, so because in some question it's sometime what happen, you will be getting the values and their units also. So with the help of the units you can determine that which thing is given to you. Okay, and same thing same way you can find the SI unit for the kb also. That is also going to be in the same way, that is m, that is molarity, okay, mole per kg, and divided by the rising temperature, that is elevation in boiling point, so it will be the same. Okay, so that is our third colligative property, that when you are going to add a non-volatile solute in a solvent, then the solution freezing point is going to get decreased. So that is how you can understand whole of this thing. Okay, so now we are left with one more colligative property that we are going to do in our next video. Okay, and we are going to discuss something about one more topic, very very important topic, abnormal molar mass. Okay, so that's it for today. So just see these videos and all the videos related to the chapter solution. Okay, and please like the video and subscribe my channel. Don't forget to press the bell icon. Okay, see you in the next video, please students.